Hello, my name is METİN Aridaşir. This is 35th part of explanation of my theory. What we will do today? Helium spectral lines, my theoretical computations and comparison with data. From this right side, data from the source NIST, National Institute of Standards and Technology. The data's source, right side completely. And left side, my theoretical, according to my theory and my formulas, my theoretical computations. I hope you can see. Okay. According to my theory and my formulas, 1. For each proton, make with only one electron motion form, joint-cyclical motion form. If in an atom, only one proton, there only one electron motion form, usually make joint cyclical motion. What we say this? Proton-bounded, atom-bounded electron motion form, which is the source of single wave pulse through affected by successive wave of free electron motion form. Again, 1. For each proton, make only one electron motion form. Make with only one electron motion form. Joint cyclical motion. 2. Each proton-tied, proton-bounded electron motion form has itself ionization energy. So, for instance, if there is 10 proton, there are 10 electron, 10 different electron, and different initial wavelength, different ionization energy for each one. 2. Each proton-tied, proton-bounded electron motion form has its ionization energy. These are according to my theory and my formulas. 3. Undisturbed, in balance, undisturbed, in balance, initial conditions. Each ionization energy corresponds each bounded electron motion form's initial wavelength. Remember lambda EI. Each one has different lambda EI, initial wavelength. Okay. For instance, for helium, there are two ionization energies according to my theory. Certain ionization energies. For greater electron motion form, i.e. 1, here, I try to draw and show. I will explain this. This is my helium model, for instance, here. Two protons have made joint cyclical motion. Two protons, okay? Don't forget this. Small, very small. Now, here joint cyclical motion between two protons, okay? One proton here, another one there, okay? For each proton, there are two electron motion forms, okay? One of in this same direction, this is electron motion form, okay? Same direction. And it has lambda EI, watt. Wait a moment. This is my helium model. Okay. I generalized this for all of atoms. Here. Another electron motion form, second. For each proton, only one electron. For first proton, this electron motion form. For second proton, now opposite direction because of naturally because of one of downside joint motion, another upside joint motion with proton, another proton, and bigger wavelength electron here. This is its direction. Understand? And here, another wavelength, so important. This is first proton. This is second, last proton, but for last one, electron motion forms wavelength, I will say first. Okay. Lambda EI1, bigger, for bigger electron. Lambda EI2, here, for smaller electron. Okay. This is helium. And for greater electron motion form, ionization energy is equal to, for this ionization ionization energy 1 equal to 24.589 electron volt for bigger one. Okay. And its initial wavelength, nothing disturbed it. Its initial wavelength lambda EI equal to hc divided by n square, but n, remember, only for bounded electron motion forms, n always equal to 1. Okay, n square lambda EI, remember, n equal to 1. It's not important. Here, lambda EI1 or lambda for which atom? Helium. Lambda EI helium 1. Okay. Equal to 51.41 nanometer. 51.41 nanometer for in helium atom joint cycle with second proton and last electron motion form, bounded electron motion form, wavelength lambda EI helium 1 is equal to 51.41 nanometer. Okay. For smaller electron, here, remember, first proton bounded, first proton tied. Ionization energy 2 for helium equal to smaller and smallest in here, helium, equal to 54.367 EV. Okay. $54.367 EV here for smaller electron motion form. And lambda EI helium 2 smaller, here smallest wavelength of smallest electron motion form in helium atom. 22, approximately 22.8 nanometer. This is so important. This is so important. If we don't know lambda, especially smallest electron motion forms wavelength, if we don't know, we cannot compute or account any spectral lines of atom according to my theory and according to my formulas. Okay, here I will show you now what I mean shortly. I hope you see. (22.8) second electron of helium. I count according to my formulas. And this is result, this is data, this is n equal 1, n equal 8. In former video, my former video, I have explained what is the n. Effective free electron motion forms, successive wave number. Remember, I advise you to watching my former video about this spectrum, atom spectra. Okay, here, n equal 1, n equal 6, second electron. Here, result. Compare, please, with data. Okay, wholly. 1 to 8, 1 to 7, 1 to 6, 1 to 5, 1 to 4, 1 to 3. Now, this was for first bigger electron motion form. Okay? Spectral line. Then again, smaller one, 22.8. N equal 2, n equal 9, n equal 2, n equal 8, etc. Okay, wait a moment, please. I will tell you again this step. Here, don't forget this. This is the model. One proton, first electron. Then second proton, second electron. But bigger, we say first electron. Smaller, last electron. Smallest, last electron. Okay, here second for helium. It has 2 proton and 2 electron. Okay. What was my formulas? Remember each spectral line is in fact single wave pulse. Each line representative single wave pulse. Remember, each line is representative, each line's size, volume is representative wavelength of single wave pulse. Remember former video. Say, what was my formula? En lambda EI equal to HC divided by n square lambda EI. Don't forget this one. Okay, then remember ENS minus ENG. What was NS? Smaller wave number of effective free electron motion forms successive wave. Okay. Here NG greater wave number of effective free electron motion forms effective successive wave. Okay. Equal to E single wave pulse energy equal to single wave pulses energy. Okay. Between n equal smaller and n equal greater. Okay. NS and G. This is my another formula, and from this we find representative wavelength of single wave pulse. Lambda EI, no, lambda representative single wave pulse, NS and G equal to HC divided by E energy of single wave pulse between NS and NG. This is my another formula. Representative frequency I don't mention. I can write a formula for this. It's not important for now. Okay. Same way. Here, representative single wave pulses wavelength between n smaller and greater is spectral line value. Okay. Lambda representative single wave pulse and S and G and S1 and S and G1, etc. here. Okay. For final result, we need this wavelength. Okay. Now, I have applied these, my formulas and my theory. Then I have predicted wholly and certainly these results for helium multi-electron atom. Almost wholly I have finished it here. For smaller, in fact, in helium atom for smallest electron motion form, 22.8 nanometer, and from one end from from n equal to 8 to n equal 1, shrinking. Okay, this is result. Compare, almost same. From 7 enlarging, okay, to 1, this is result. Okay. How did I count for this n? Wait a moment, please. Don't forget n square. Okay. Enlarging, say its initial wavelength, and when free electron motion forms, this is atom-bounded electron motion form, atom-tied, and here come in free electron motion form successive way, which n equals, say, 4, but we say n square lambda EI 22.8. Okay, 2. Okay, 16 lambda EI, say 16 lambda EI. 2 shrinks again, not initial, maybe shrinks to n equal, here n equal 4, to n equal 2, shrinks n equal 2 base step, not wholly shrink because of another successive wave coincide that, and stay that n equal 2 when another free electron motion forms, or same, I don't know, it's not important, we don't know, come in again. Before it is before arrive its initial wavelength, coincide and equal to wave. Okay.